LHC machine is known for its 4 main experiments: Atlas, CMS, LHCb, and ALICE. But actually, that's not the whole story. The LHC has also other experiments, and one of them is TOTEM, and it has the special feature of being placed all around the interaction point. Parts of TOTEM are in the tunnel. TOTEM's components are scattered around LHC.5. 2 of its subdetectors are placed in the CMS cavern and 2 on each side of the cavern in the accelerator tunnel. I'm here with Carsten Eggert from Germany. He's the spokesperson of the TOTEM experiment, and now we're going into the tunnel to take a look at one of the most important parts of this detector. Is that right?
That's right. It's a pleasure to go with you in the tunnel, Paula.
Okay, let's go. Wow.
So what makes TOTEM special is that 2 of its main subdetectors, called the Roman pots, are placed right in the LHC machine tunnel 220 meters away from the interaction point, within 1 millimeter of the beam pipe. Carsten Eggert explains why TOTEM's Roman pots are so close to the beam pipe and so far from the interaction point.
With TOTEM, we have 2 detectors which are at the intersection point to measure all the particles which come out in the forward direction. But here we have some special detectors which measure protons which are very close to the beam pipe. You see, the beam here has a size of 1 millimeter or so, and we go with our detectors here in the forward direction very close to the beam pipe, within 1 millimeter. You can imagine with such intensive beam that is not an easy task to do. TOTEM is a small experiment compared to the big ones like Atlas and CMS. We have 1% of people, typically 100, who are working there. But what is special in TOTEM is that we would like to measure the total cross-section, namely the probability that 2 protons interact with each other. This has a long history at CERN because the first discovery were done at the ISR more than 50 years ago, when people recognized that the total cross-section is increasing with energy. And that's also relevant for the cosmic ray interpretation, where you need these total cross-section measurements. Now, the other part of TOTEM is that we want to measure interactions where the 2 protons mainly go forward. Either they scatter elastically, like you do in billiard, for example, they touch each other very slightly, or they lose a little bit of momentum, and then you produce new particles. You have a smaller interaction because the protons take the whole energy in these 2 beam pipes in the forward direction, and you have a few gluons making an interaction. It's almost like a glue machine. It's the first time that with this high precision we can measure that, because we have already done this kind of physics over 50 years, but never with this kind of precision.
But I thought we knew everything about the proton. Its mass, its spin, its cross-section. Aren't these known values?
I am going to contradict you a little bit. How it looks inside of the proton, we don't know much. The proton may change with velocity. So if the energy is higher, the proton may be completely different than if you have a proton at rest. So we don't know much what is inside if the proton interacts as a whole. And that is one of the things which we are going to study. Of course, the big experiments make part-on-part-on scattering to produce new particles, very, very detailed. But the global feature of the proton, we don't know so well. What happens with the proton when it gets energy, it becomes larger. That's the first thing. The second, what happens is it becomes darker. So if it is darker, it has more interaction probability. Clear. If it becomes larger, it has more interaction probability. So it's a very important point to see how the cross-section increases with energy in itself, to understand the proton which goes with a very high velocity, or which has a very high energy. On the other hand, it's also important for cosmic ray studies. Remember, for example, the Auger experiment is measuring protons or other particles coming in our atmosphere, and they claim that they may see point-like structures. But then these point-like structures should be protons, otherwise they cannot be point-like. So again, and to identify whether these are protons or whether these are iron or other elements, you have to know the total cross-section, because you have to know where it starts in the atmosphere. Okay, so it's a very important part. So we are very eager to be the first to get some good physics results.